If you would recall, we have been telling the story of convergence of series. And today we want to take a quick detour into geometric series. I kind of waved my hands at it when we talked about the integral test because we can use the integral test to determine if the conditions under which a geometric series converges. We already know the important stuff about a geometric series. A geometric series converges if its common ratio is less than 1. And furthermore, we know that the sum of a geometric series is the first term divided by 1 minus the common ratio. So we should note that the A in the A over 1 minus R is specifically the first term of the series starting at 0. So if we had, for example, this numerator in the sum is the first term, not just the coefficient. So if I had the sum as n goes from 5 to infinity of a times r to the n, then the first term would be ar to the 5th. And so in the sum, the numerator would be ar to the 5th over 1 minus the common ratio. I didn't specify an r yet again, so this is if the common ratio is less than 1 in absolute value. So the numerator in our formula for the sum of the geometric series is the first term. The numerator in the formula for the sum of a geometric series is the first term and not just the coefficient. As far as determining if the geometric series converges or diverges, you just have to look at the common ratio. But if we actually want to know what that sum is, since we want a much more specific piece of information, what is the sum of this geometric series? You got to use the first term, not just the coefficient. Otherwise, we'll be off by, well, these first 4 terms. That detail aside, we already have all the information we need about geometric series. Question? Yeah. The denominator is always 1 minus the common ratio. All right. So I want to stop and look at this in a little more detail because it's kind of cool. So let's just actually just calculate some stuff. So for example, if I have the series as n goes from 0 to infinity of 3 times 0.1 to the n. Here we start off at 3 times 0.1 to the 0 plus 3 times 0.1 to the n. Plus 3 times 0.1 to the n to the second, and so on. The first term here is a 3. And we divide this by 1 minus the common ratio. So we're not surprised that this comes out to 3 1/3 because we can see that we're just building the 0.3 repeating by taking 0.1 to the n, 0.1 as our common ratio. Sentence is difficult to do. So we can see here's the 3, and then here is the 1/3. So it's 3 1/3. So if I start this series later, if I start the counting at 1, we're not chopping off terms that are important to convergence versus divergence. We're just chopping off terms that are important to the sum. So this series is going to have, as a first term, 0.3. So now that the first term is 0.3 over 1 minus 0.1, 0.3 divided by 0.9 is just the 1/3. So where the series starts is not a concern as far as convergence versus divergence, but it is a concern as far as the sum of the series. So in our formula for the sum of the series, the A represents the first term, not just the coefficient. Furthermore, we can clearly see that if the terms of the geometric series don't go to 0, then our geometric series is going to expand towards infinity. So if the common ratio, if this number is anything even slightly less than 1, then the terms will go to 0 fast enough, and we'll have A over 1 minus R. If our common ratio is greater than 1, even if it's only slightly greater than 1, let's not go so, you don't have to go so big. Always so excessive. Even if we take $5 and invest it into an account that will pay only 1%, eventually it will become an infinite amount of money. Probably not before we're dead, unless we have an infinite lifespan, but this is clearly going to be an infinite sum. We wouldn't say that the series is infinite. That's really weird. We would say that the series diverges. We could say that the limit of the terms is infinity, but that means that but only under the understanding that the limit of the terms going to infinity means that the limit of the terms does not exist. But if you said the limit of the terms is infinity, everybody will know what you mean, even though it technically doesn't make sense. Infinite money with one simple trick. Live forever. So even though we already know to find what the sum of a geometric series is, it is still an interesting question to find the sum of a geometric series. We're going to start with a finite geometric series. We're going to start with a finite geometric series. I said finite, so not infinite. I'm going to make it look a little different by indexing with I. So I started my counting at 0. So, and I wanted n terms. So I'm counting from 0 to n minus 1. So this is the sum of n terms. I can only ever think of this in the style of Picard. Originally, that whole episode was not Picard being tortured by Kardashians, but Cardassians, not Kardashian. That's a completely different show. He was having a discussion with the master teacher. And said, let's punch this up a little bit. Because then it'll be more imperative to rescue it. Or maybe it'll be less imperative rescue it. So we have n terms in our geometric series. And since this is a finite geometric series with only n terms, it definitely has a sum. And I'm going to call that sum S. So S is the sum of this series. Up next, we're going to take this equation and I'm going to multiply everything by R, the common ratio. So on the left, in this equation, we end up with AR plus AR squared plus AR to the third and AR to the fourth. And this goes all the way up to AR to the n. Over on the other side, we still just have R times S. It just bumps up the exponent by 1 all the way through. Now what we're going to do is subtract. We're going to take our sum S and we're going to subtract R times S. So take S and minus the RS. So here are my terms from S, A plus AR plus AR squared plus AR to the third. And we're going to be subtracting this series in blue, which starts with an AR and has an AR squared and an AR to the third and an AR to the fourth. The last term from S is AR to the n minus 1, but that's the second to last term in the RS sum. Because the AR sum, or sorry, the RS sum goes all the way up to AR to the n. So we see that when we subtract the RS sum from the S sum, almost all the terms cancel out. All that's left is the first term of the S sum and the last term of the RS sum. So all that's left here is an A minus AR to the n. Everything else cancels out. Now we can see that we just need to solve for the S. And here's where we can see that 1 minus R showing up as a denominator. So if we factor the S out of the left, we're left with S times 1 minus R. And we can also factor an A out of the right side. That'll leave A minus A times 1 minus R to the n. And so this tells us that S is equal to A times 1 minus R to the n over 1 minus R. Now, this is the sum of a finite geometric series, so this one does not care the value of R. This is a finite sum. This will work for any value of R. But if we want the infinite sum, if n goes to infinity, then this sum only becomes finite if R is less than 1 because of this factor, or sorry, this term, R to the n. So as n goes to infinity, r to the n goes to 0, but only if r is less than 1. So here's one way we can get at our sum of an infinite geometric series. So here in this term, if r is less than 1 in absolute value, then the limits as n goes to infinity of this r to the n is equal to 0. And we not only get the conditions under which an infinite geometric series will converge, we also get a formula for the sum of that. So that's pretty cool. Well, like this involves a little bit of algebraic sleight of hand. Just take the sum, multiply it by something, and then subtract those two to kind of scoop out the middle, all those middle terms, and just look at what's going on at the ends. A lot of cool parallels between doing stuff like this, just looking at what's on the ends by doing something to get rid of the stuff in the middle. Just look at the ends. A lot of nice parallel between that and integration. Pretty cool. There's another thing that we can look at. Now that we've got this 1 minus r to the n over 1 minus r, we can also invoke some algebra. If we think about some rational functions, we know that if we have the rational expression 1 minus x squared over 1 minus x, we can cancel out, we can factor the numerator. And we're left with the 1 plus x. Furthermore, if I change this to, instead of 1 minus x squared, if I have 1 minus x cubed, I can factor the numerator. If we remember our difference of cubes formula, which I'm sure we all do. But notice what happens after we divide out the 1 minus x. We're left with 1 plus x squared. And if all this is looking familiar to what we just did, it's supposed to. That's why I'm doing this now, to point out how closely this is related to just the algebra topic of simplifying rational expressions. We can do one more, because I'm betting we know one more. If we have 1 minus x to the fourth over 1 minus x, when we factor 1 minus x to the fourth, it factors to 1 minus x squared times 1 plus x squared. And then we can factor the 1 minus x squared to 1 minus x and 1 plus x. This allows us to cancel the 1 minus x, and we're left with 1 plus x times 1 plus x squared. And if we multiply this out, we get 1 plus x squared plus x to the third. In the same thing, which is the same thing that we had in our geometric series. If we keep going, 1 minus x to the fifth over 1 minus x, the same thing will happen. Some stuff happens. We could use long division, but no one ever wants to do the long division here. I don't know why. It's so much fun. But since we're at the bottom of the page and we're out of space anyway, do the long division, you'll find that this becomes 1 plus x squared plus x to the third plus x to the fourth. So this geometric series has a pretty cool connection to polynomial way back from. This means if you want to teach people about investing and they don't have calculus for geometric series, you can always just fall back onto algebra. I'm just kidding. For the most part, if you're trying to explain investing to someone, just say, start investing now. It'll pay off better in the long run. Investing for 60 years is better than investing for 20 years. And if people are like, oh, I can't afford to put $20 a month away into a retirement account, just remind them that they can not afford not to. And if they're like, oh, show me, then just be like, oh, it's going to mean algebra. It's going to be some algebra. Then they'll be like, oh, all right, I'll just take your word for it. And then ignore you and wonder why they're broke. Any questions? I'm just kidding. That's completely unfair. To shift the responsibility of the care of our elderly onto the elderly themselves. That's a dick move on our part. We should just take care of these people. They are our elders. If you're worried about what they did to do, what they did to deserve it, they fucking exist, and so they deserve care. How about them? So by saying, well, you should have invested, it's just saying, well, I guess you didn't plan ahead, so you get to die now. Big move. What kind of fucked up society would do that? Oh, that's right, ours would. Anyway. All right, so that's a quick trip into geometric series. We now have a formula for the sum of a finite geometric series. So this is where A is our first term of the series, R is the common ratio, and N is the number of terms in the series. So if we wanted to say, figure out what would happen if we invested $10 per month at 1% growth for 60 years, what would that produce? We can calculate that. Spelled month wrong. Nominally, this would be like 12% per year, which is kind of a lot, but it's not that far off of, say, 10% per year, which is your long run average. Just like very simple things. So if we wanted like $10 per month at say 1% per month for 10, 20, 30, 40 years, starting off at 0. So this could be our A. If it's increasing by 1% per month, our common ratio will be 1.01. And then we'll have a bunch of values for N. So 10 years is 120 months. So N equals 120. Oh shit, forget to keep this with. Grab the calculator. So it doesn't seem like too big of a deal, $2,300. You're like, oh, dude, that's $2,300. That's only over 10 years though. And what did we put into it? So if we subtract 10 times 120, so that's 1,100 over what we put into it. Let's do this for 20 years. So it'd be like retiring at 60 and starting at 40. This is also not going to be very good. We just have to change the 120 to 240. 98, 92, 55. So this is the total. This includes all the stuff that we put in, and we've put in $10 240 times. So that's a plus of 74.92.55. Let's do this again for 360. Representing 30 years, retiring at 60, but starting at 30. 34, 949, 64. The increase here is 10 minus $10 times 360, 349, 64. The amount that we're getting out is growing exponentially. The amount that we're putting in is still growing linearly. Now, this is only $34,000. But we've only put in $10 a month for 30 years. Hopefully, at some point, we've increased that $10 to something else. So here at 480, this would represent retiring at 60 and starting at 20. For a lot of you, that's starting a couple years ago or starting now. Minus what we put in, 112, 847, 73. Now, once again, this is not enough money to retire on. You need about $2 million to stop working sometime in the 60s, depending on how long you plan on living. You could go with the brand new millennial retirement plan, which is just to like die at 60 while you're still working. And you never have retirement. Now, this is clearly not enough, but this is once again only $10 per month. And at some point, hopefully in the future, you'll be making more money than you are in your 20s. And so you would only do this $10 for like 10 years and then switch this 10 up to something larger. Notice that the amount that's being put in, that is just a factor on this whole thing. So if you double that amount, if I change that 10 to a 20, that just doubles the entire amount. It doubles what we're putting in, but it just doubles the total because that A is a multiplier that we can factor out of the entire polynomial. The growth is happening in the rational function part, 1 minus r to the n over 1 minus r. That's where the growth is happening. It's just going to be multiplied by whatever we're putting in every month. But that 235 is double the 117. So you might think, I can't afford to put $10 a month, a month. $10 a month. I can't afford to put $10 a month away that I won't be looking at for the next 40 years. But on the other hand, can you really afford not to? Because what if you start now and keep going until 70? So 600. Just 10 more years, and we go from 235 to 781. Now, this is 1% per month growth, which is a little bit heavy. So we want to cut that down to say, like, maybe what if we go for 10% per year or 8% per year if we want to be more conservative? But you want to think in terms of the long run. You just put it away and you wait. And when things fade, you just ride it out because they'll come back up again. This is more reliable than cryptocurrency, which is just a different form of gambling. Long-term gambling is you're acting like the casino. Short-term gambling, you're acting like the gambler. You might be the lucky gambler who comes out ahead, but in the long-term game, in the long game, you want to be the casino. You want slow, reliable growth. Don't be the gambler, be the casino. Does that make sense? Then at a certain point, once you're putting up enough money to have $2 million or the equivalent 40 years from now, it wasn't $2 million 40 when I was 11, but $2 million 4 years from now. Once you have that set up and that plan is working, then you could start taking a couple bucks per week and buying a lotto ticket because that's just fun. Really annoyed when mathematicians like, oh, well, I'm a mathematician, so I don't buy lottery tickets. So I go, oh, you sound like a puritanical stick in the mud who doesn't like gambling because it's fun. Because it's gambling. If you think about the lottery ticket as a retirement plan, you're being an idiot. If you think about lottery as a fun little gambling activity, then that's fine. So long as you can afford $2 per week to buy yourself a lottery ticket. If you can't afford $2 per week, now you're being stupid. Because in gambling, there is one concern. Can I afford to lose this bet? The answer is no, then you don't place the bet. The answer is yes, but fuck it, do it. You know what I mean? I only play the lottery when it's going to be a positive return. It still doesn't mean you're going to win. You're still burning money anyway. It's gambling, you idiot. Learn to gamble. It's those same kind of people that don't understand the trolley problem, for fuck's sake. So that's going to do it for today. I will see you all on the morrow. Everybody have a good day. Start a retirement account. And thanks for playing.